Assalamualaikum and a very good day to our Professor Rina. We are from Group 2. Would like to present about our group assignment, which is titled Utilizing Hemocellulose from Rice Straw Waste in Automation, Converting it to Cellulose via the pentose phosphate powers into xylitol, a high-value sustainable sweetener. So first of all, I would like to introduce to our group members, which is me, Amir Ashraf, Danish Hakim, Hafiz Akwan, and Muhammad Fidaus. So without wasting any time, I will pass the introduction to Zach.
Now we start our presentation with what we are learning today. So our presentation consists of four sections. The first one is for the part one is introduction, pronoun statement, and rise of straw waste issue. The second one is enzyme engineering and metabolic pathway. The third one is yield calculation and also a carbon audit. Last but not least is sustainability, biosafety, reflection, and also the conclusion. Okay, everyone. For the part one is my part. So I will introduce to you about our introduction of our project. Our project is focused on converting a raw straw waste into the xylitol using metabolic engineering. So we know in Malaysia, we produce approximately 2 million tons of rice straw every year, byproduct of paddy cultivation. However, only a small portion of biomass is utilized, while most of it is properly burned and left to, to decompose in agriculture field. So, Rastra is rich in lignocellulosic components, particularly hemicellulose, which account for about 25 to 35% of its dry weight. Throughout the hydrolysis, hemicellulose can be converted into D-cellulose, a 5-carbon sugar that serves as the precursor for xylitol production. Therefore, rice straw represents a valuable renewable feedstock that can be transformed into the high-value product throughout the metabolic engineering. So we can see the rice straw contains cellulose around 52 to 47%, hemicellulose around 25 to 35%, and also the lignin between the 15 to 24%, and can be converted into the rice straw into a xylitol crystal by using the metabolic engineering process. Okay, now we move to the problem statement for our project. Despite its goodness, the rice straw remains an underutilized agricultural waste. Currently, open field burning is still widely practiced, but it can due to some of pollution or climate change for our environment like air pollution, haze and greenhouse gas emission like CO2 and also methane. So when the rice straw is left in the field, it decomposes and releases methane, which has a much higher global warming potential than carbon dioxide. At the same time, conversion of xylitol production relies on a chemical hydrogenation process that requires a high temperature, high pressure, and also the expensive catalyst that making the process energy intensive and costly. Therefore, there is a need for some of sustainable approach that can simultaneously solve the rice straw waste problem while producing a valuable product like the xylitol, and also can have a some of green and sustainable process that can be do. And one of the solution is to be utilize the engineered microorganism to convert the rice straw derived into cellulose and also the xylitol. There are some of the waste issue related to the rice straw. So I will highlight to you 3 issues that can be identified in the rice straw in our country, Malaysia. So rice straw disposal create several environmental and economic issue. First, open burning contribute to the significant to air pollution and greenhouse gases emission. This practice affect air quality and can impact the public health in surrounding community. Second, when the rice straw is left to decompose naturally, methane gas is released into the atmosphere. Methane is potent greenhouse gases that contribute to the global warming. Third, is valuable biomass resources are wasted instead of being utilized for production application. Rather than treating the rice straw as a waste, it can be converted into the D-cellulose and subsequent into the xylitol. This approach aligns with the circular bioeconomy principle by converting the agriculture residue into the value-added product like xylitol and also another like maybe from the methane we can convert into the biodiesel or biogas.
The metabolic pathway begins with the pretreatment and hydrolysis of rice straw to release the D-xylose from the hemicellulose fraction. Inside the engineered microorganism, D-xylose is converted into xylitol by the enzyme xylose reductase, which is encoded by the XYL gene. In the natural pathway, xylitol is further converted into D-xylulose by xylitol dehydrogenase, encoded by the XYL2 gene. This reduces xylitol accumulation because the product continues to enter the pentose phosphate pathway for cell growth. To maximize xylitol production, we overexpress the XYL1 gene to increase xylitol formation and knock out the XYL2 gene to block xylitol consumption. In addition, NADPH regeneration is enhanced to provide sufficient reducing power for the reaction. As a result, carbon flux is redirected towards xylitol accumulation, leading to higher yield, reduced byproduct formation, and improved process efficiency. So the figure shows the difference between the native and engineered pathways for xylitol production. In the native pathway, D-xylose is converted into xylitol by xylose reductase, or we call as XR. However, the xylitol is further converted into D-xylose by xylitol dehydrogenase, which is the XTH, and eventually enters the pentose phosphate pathway for cell growth. This will reduce the amount of xylitol produced. To overcome this issue, we engineered the pathway by overexpressing the XR gene, which is the XYL1, to increase the conversion of xylose into xylitol. At the same time, the XDH gene, the XYL2, was knocked out to prevent xylitol from being converted into D-xylulose. As a result, carbon flux is redirected towards xylitol accumulation and also leading to higher yield and higher productivity and also reducing the byproducts.
Hi, so my part is the stoichiometry check. I will be presenting about the theoretical efficiency of converting D-xylose into xylitol through the stoichiometry analysis. So as you can see at the top here, there's a bioconversion reaction which represents the reduction of D-xylose into xylitol using NADPH as the reducing factor. So the metabolic pathway it is modified so that the xylitol production becomes the preferred route. So as shown in the slide, the reductase encoded by the SYL1 genes convert D-xylose into xylitol, while the competing SYL2 gene was removed to minimize the further conversion and improve product accumulation. So to evaluate the production efficiency, the theoretical yield was calculated based on the ratio between product mass and substrate mass. So as you can see the table here, the molecular weight of D-xylose is 150.113 gram per mole, and xylitol has a molecular weight of 152.15 gram per mole. So if when you substitute those values in the yield equation, you get 1.013 gram per gram. So that means 1 kilogram of xylose or 1 gram of xylose can produce approximately 1.013 gram or kilogram of xylitol. So now I'm going to present about the carbon audit, which consists of two parts: carbon conversion efficiency (CCE) and net carbon footprint (CF). So first, we're going to start off with CCE. As you know, before we have evaluated the conversion efficiency. So now carbon auditing is performed to determine how effective it is to retain to retain the carbon and estimate the environmental impact. So it is first calculated using the ratio of moles of carbon present in the product to the moles of carbon present in the feedstock. Um, yeah, it's shown in the equation here. Moles of carbon in product per moles of carbon in consumed feedstock times with 100%. So since both xylose and xylitol contains 5 carbon atoms for both, so the carbon's balance become 5 per 5 times with 100%. So the CCE is equals to 100. It is theoretical CCE. So this show that according to the stoichiometric analysis, all carbon atoms entering the reaction may remains in the product from the reactant. Also mean that there is no losses of carbons during the process reaction. However, this value represents the ideal upper limit and does not fully represent the industrial operation, because in the actual production, some carbon might be diverted or lost toward microbial growth, side product formation, and as you know, entropic conversion and other things. So next is the net carbon footprint. This net CF consists of three components, which as you can see, the stoichiometric carbon dioxide and process, which is the direct carbon dioxide generated from the reactions, emission from the process operations, and carbon sequestration measures. Although the biochemical reaction does not release the carbon dioxide, but the emission still will happen from many things such as pre-treatment, fermentation, and energy consumption. So after looking at the carbon recovery and sequestration strategies, the net CF is estimated as 2.2 kilogram of carbon dioxide, equivalent to the kilogram of xylitol. This is taken from um, a journal which is Santos and Colombo.
Next, I will explain the Living Modified Organism (LMO) regulatory framework for our proposed xylitol production process. Our process uses genetically engineered microorganisms to convert xylose from rice straw into xylitol more efficiently. Because these organisms contain modified and genetic material, they are classified as LMOs. While they improve productivity, biosafety measures are required to protect human health and the environment in line with the Cartagena Protocol on Biosafety. So first is on the physical containment. The microorganisms are grown in closed stainless steel bioreactors to prevent environmental release. HEPA filters is used to remove the microbial aerosols from exhaust gases, and all liquid and solid waste are sterilized before disposal. Second one is biological containment. For this part, we propose an autotrophic strains that depend on specific nutrients absent in nature, preventing survival outside the facility. Suicide genes systems can also be used to trigger cell death if escape occurs, and non-pathogenic host strains further reduce risk. And finally, monitoring and compliance. So as you can see, our regular genetic stability testing, environmental monitoring, and emergency response plans are implemented. The process also it complies with the Malaysian Biosafety Act 2007 alongside international guidelines. So overall, this physical, biological, and also monitoring and compliance controls ensure safe and responsible xylitol production while supporting sustainable industrial biotechnology. Okay, so next I will explain the circular loop in our rice straw biorefinery system. The circular bioeconomy model maximizes resource use and minimize waste by converting rice straw into multiple value-added products instead of treating it as waste. So as you can see from figure 2.3, the main product is xylitol. Rice straw is pre-treated and hydrolyzed to release xylose, which is then converted into xylitol via engineered microbial fermentation. Xylitol is a high-value, low-calorie sweetener used in food, pharmaceutical, and also oral care applications. For byproduct utilization, lignin is used as boiler fuel for steam and electricity generation, improving energy self-sufficiency. The microbial biomass is reused as biofertilizer, returning nutrients to paddy fields. Residual solids can also be converted into biochar, which improves soil quality and acts as a long-term carbon sink. Overall, this integrated system reduces waste, recovers resources, lowers greenhouse gas emission, and also support a zero waste biorefinery concept. It demonstrates how circular economy principles can turn rice straw into a valuable renewable resource while supporting a low carbon bioeconomy. Lastly, I will discuss the socio-economic and environmental impacts of our proposed biorefinery. From a social perspective, farmers can earn additional income by selling rice straw instead of treating it as a waste. The project also reduces agricultural waste disposal problems, creates green jobs in biomass processing, and supports rural economic development. Environmentally, the process reduces open field burning of rice straw, improving air quality and also lowering the greenhouse gas emission. The biochar produced can enhance soil fertility while reducing the need for chemical fertilizers. Overall, it promotes efficient use of resources through waste valorization. This project contributes highly in SDG 9 through green industrial innovation, SDG 12 through in responsible production and waste reduction, and SDG 13 through climate action and emission reduction. So that is all from us. Thank you.